All right, so now we're going to shift gears a bit. Now we're going to talk about relative motion. So like if you're driving a car and I'm driving a car also and you're going faster or slower than me, I might ask, what is your speed relative to me? Or somebody at the street sitting there might say, what's the speed of the car relative to him or something like that. Just relative motion, okay? All right, so the first thing we're going to talk about is Galilean relativity. So that's really what we discuss in Physics 121. It just means that the speeds involved in a problem are much, much less than the speed of light, okay? And I'll explain later why that's important. All right, so here's a question for you. You're driving to town on H3. The speedometer in your car reads 45 miles an hour. I am also driving to town on the same section of H3, and since you are driving so slowly, I pass you. The speedometer in my car reads 60 miles an hour. What is my real speed? So please come up with an answer. Pause your video and come up with an answer. Okay, what is my real speed? It's a meaningless question, right? I mean, relative to who? Relative to what? Relative to the person on the street? Relative to me? Relative to somebody on the other side of the universe? What? You got to say relative to what, okay? So objects move relative to a reference frame. That's the thing. Objects move relative to a reference frame. So here's a physics joke. It's a good one. All right, so top. Mommy, what is the fastest animal? Normal person. The cheetah. Biologist. A descending peregrine, or whatever, falcon. Engineer. Human being in an orbiting satellite. Physicist. Unspecified reference frame. Question invalid. I hope you get that one. Okay, here's another question for you. Okay, let's draw it. So Velma in a train moving eastward. So here's a train, just pretend, all right? So the train is moving eastward at 70 meters per second. So Velma throws a ball toward the rear of the train. So here's Velma. So she throws a ball to the rear of the train at 20 meters per second. All right. Now here's Mort. Okay. So there's Mort. So the velocity of the ball relative to Mort, who is standing beside the tracks, is what? So pause your video and figure it out. Okay, the answer is 50 meters per second eastward. And I think that's just logical, right? Because, I mean, like after 1 second, the train has moved that way 70 meters per second, but the ball has moved that way 70 meters. The ball has moved 20 meters. So, I mean, relative to the train, right? Relative to the train. So relative to the road, relative to Mort, it's moved 50 meters that way. So the speed would be, because it was 1 second, 50 meters per second. Okay, so I hope you can just figure out this logically. We're going to have a formula later on, but just logically you should be able to figure it out. All right. Okay, now we're going to come up with this awesome equation. So what is the velocity of the runner relative to the observer? Okay, and look at all these subscripts. So pause your video and figure it out, please. All right. So the velocity of the runner relative to the ground is the velocity of the runner relative to the train plus the velocity of the train relative to the ground. It kind of makes sense, right? I mean, let's say you're in a car. Okay, let's say your car is going 60 miles per hour that way, and then no air resistance. It's convertible. All right, and then you stand up and you throw a ball 100 miles per hour that way. What's the speed of the ball relative to somebody standing on the ground? 160 miles an hour, right? That's exactly what that says, all right? It makes a lot of sense. Okay. Now, here is the really neat equation. And we're going to actually use this equation in Physics 221 when we talk about relativity. And it just makes life a lot easier than otherwise, all right? Okay, so again, the velocity of the runner relative to the ground is the velocity of the runner relative to the train plus velocity train relative to the ground. Okay, no kidding, right? But here's a little trick. Okay, notice you have the runner on the left, and here's the runner on the left. Here you have the ground on the right. You have the ground on the right. Here you have the T's, the train, kind of in the middle. So just kind of think that they cancel. All right. So that's how you do it. That's always how you do it. Okay? If it's 2 or 3 dimensions, A's on the left, A's on the left. B's on the right, B's on the right. You just kind of imagine that these things are canceling. It's a silly little formula, but it works. And again, it works when we do relativity. So it's totally cool, you know? So let's do this. Okay? Don't look at this. All right? So we want to get the velocity of the ball relative to Mort, okay? So let's do it with a silly little rule. Ball's on the left, ball's on the left. Mort's on the right, Mort's on the right. These guys have to be the same because they cancel, all right? So, I mean, what do we know? You know, we know the speed of we know the train, right? The train. So we put a train here. Okay? So let's do it. So what's the velocity of the ball relative to the train? It's minus, right? It's minus 20 meters per second. Why is it minus? Because it's going that way, right? It's going that way, right? Because she was facing the rear of the train. What's the velocity of the train relative to Mort? It says it right there, 70 meters per second. So what's minus 20 plus 70? 50. Okay? So, I mean, so this is an awesome equation, you know, this thing. I mean, sometimes they'll have a word problem that they word so completely confusing, and if you just use one of these equations, you'll get it. You know, you'll totally get it. If it's so confusing you can't, you know, like figure it out with logic, just use the equation. You'll get it. So it's really nice. Okay. Here's something that we'll use kind of here and there. Physics 121, Physics 220, Physics 221. It's the concept of an inertial reference frame. Inertial reference frame, it's just, what's a reference frame? You know, like if we did an experiment in this room, the room would be our reference frame. Okay? If you did or maybe even the Earth, that would be fine. How about if you did an experiment in a moving jet? Then that would be your reference frame, okay? All right, so an inertial reference frame is a special reference frame. It just means it's not accelerating. So whenever you hear the word inertial reference frame, it's not accelerating. Okay, that's all. Now, it's easy to, so here you have 3 terms, right? Now let's go to this. I have 1, 2, 3 terms, okay? Now, the inertial reference frame, again, there's no acceleration, so it's constant, right? You can always pick it out from these 3 terms because it's the term that does not include, you know, the object. So what's the object? It's the runner, right? That's what we care about, the speed of the runner. Well, notice this is the velocity of the train relative to the ground, okay? So it doesn't involve the runner, okay? So like the train, okay? We're always going to assume the train is moving at a constant velocity. So keep that in the back of your head. Inertial reference frame acceleration is 0, because you're going to see it again and again and again. All right, now, yeah, okay. That's inertial reference frame, right? Doesn't include the R for the runner, the object. Okay, now, so, we have this nice relationship with the velocities, right? So, I mean, if you want to get technical about it, you can just integrate it, right? And this would be the relationship between the distance, or I don't know, the positions, right? Yeah. Okay, the position vectors, right? So R, S on the left, G on the right, T's cancel, all right? Same silly question. So that's the relationship between the position vectors. Now here, sorry, I changed it. I put sprinter instead of runner, sorry. And the reason I did that, because I didn't want to have an R here and an R here, because it looked weird, right? So I put S for sprinter, okay? But that's the thing. I guess I could have put X's, right? X's or something like that, whatever. Okay, now, here's something that's kind of exciting. How do we get, so we got the position, the velocity. How do we get an equation for the acceleration? Well, how do you get an equation for the acceleration? Take the derivative of the velocity, right? Okay, so here's the velocity. So I have VSG equals VST plus VTG, right? And I want to take the derivative. So I just be lazy how I write it, right? Take the derivative of both sides, okay? So the derivative of that is A, sprinter relative to the ground. The derivative of that is acceleration, sprinter relative to the train. Wait a second, what's the derivative of that? Remember, this is constant, right? That's the inertial reference frame. So what's the derivative of constant? 0. Okay? So that's really important. Sorry. We're going to use that big time in Physics 220. I don't remember if we use it in Physics 221, but I just don't remember. But I know we use it in Physics 220, so that's a big deal. Okay, it's a super big deal. Okay, now we're going to do some relative motion problems, and I'm going to do them 2 ways. I'm going to do the first method, just kind of using logic. Use your head, right? Then the second one, the second method, I'm going to use our great equation, all right, which always works, okay? So let's do it logically first. Might as well. Okay, so this is American football. A wide receiver is running due north down the field at 10 meters per second. So let's say this is north. All right, so we have a wide receiver. 10 meters per second, due north. The quarterback throws the ball to him. The ball has a speed 35 meters per second, but it's moving in a direction 20 degrees east of north. So there's north. We want 20 degrees east of north. All right? So there's, okay, so that would be, that's north. But the ball is something like this. So this is 20 degrees, and it's going at 35 meters per second. So this is the ball. All right. The question is, what's the velocity of the ball relative to the wide receiver? Okay? So remember, this guy's already moving this way, right? So we want to know the speed of so this is relative to the ground, right? But we want to know the speed of the velocity, speed and direction, this relative to that, okay? Okay, so in my opinion, if you want to do this logically, the best way to do it is to split everything up into components, all right? So, okay, the wide receiver is perfect. We don't need to change that, right? Because it's already, it's along our north. We don't have to mess around with it. This is the trouble one, okay? So what are we going to do with that? Well, what do we always do, so this is 35 meters per second. This is 20 degrees. So what we want is we want the component going this way and the component going that way, like we always do, right? Okay, so what is, whatever. So what's that? Well, it's opposite, so it's sine. So it's 35 meters per second times sine of 20, and that is 12 meters per second. Okay, what's this? That's adjacent, so it's cosine. So it's 35 meters per second times cosine of 20, whatever. And that is 32.9 meters per second. All right? So I could draw the ball. I would say the ball has a velocity component this way of 32.9 meters per second, and a component going that way of 12 meters per second. Okay? It's really useful to do that. All right. Now what we want to do, okay, again, this is relative to the ground, right? It's all relative to the ground. But now we want to say, what is it? What's this velocity of the ball relative to the wide receiver? Okay. All right. Oops, sorry. Okay. Now, look. The ball is going 32.9 this way relative to the ground, but the receiver is going 10 meters per second that way relative to the ground. So according to the wide receiver, what is the velocity, what's the speed of the ball going north? Well, just that minus that, right? Agree? Agree? Think about it. If you're going 10 meters per second that way, and there's a ball going 10 meters per second that way, you just see the ball going along with you, right? Okay. So that doesn't look really straight. Okay, so relative to the wide receiver, the ball is going 22.9 meters per second that way, all right? That way. Okay, how about that? Does that change? No, that doesn't change because the wide receiver is not going that way. He's going that way, right? So that doesn't change. So that's still 12 meters per second, right? Okay. All right, so therefore, what is the velocity relative to the wide receiver? Well, good old Pythagorean theorem, right? So the velocity, is 22.9 meters per second squared plus 12 meters per second squared, square root of, and that's 25.9. Which seems reasonable, right? Nothing wrong with it. Okay, now let's do the angle. Okay, so here's the angle. All right. So opposite over adjacent tangent. So theta equals tan inverse opposite over adjacent. And that comes out to be 27.7. Ta-da! There you go. Okay, so the only thing that we really had to do, draw the picture. If you have something that's not along the coordinate planes, just resolve it like we've done before, and then just use your head, right? Just the speed of the ball relative to this guy, you just set that minus that, and just do it. Okay, so that seems sort of nice, reasonable. Now, let's just pretend that the question was really worded difficult, really in a weird manner, and we didn't want to, logic is too hard, and, we just want to use the formula, all right? And you'll see, especially when you get to relativity, my gosh. All right, so let's use the formula. All right, so there we go. Just try to erase everything. We're going to use some of the results I just erased, but that's okay. All right. So now we're going to use, and again, the formula uses vectors, right? The formula uses vectors. So now we've got to use vectors, okay? Vectors. All right. So here we go. So we're going to say, we're going to use I, J, K, right? No K, but, right? Just I and J. So J is north. Okay. Okay. So we're going to say that the velocity of the runner relative to the ground, okay, that's 10 meters per second, right? I'm not going to use, So 10J, all right? I'm going to be lazy, right? I'm going to say MKS units are assumed, all right? So I'm not going to write meters per second. Sorry, bad example. All right, so that's cool. Now, all right, but like the ball, let's do the ball. So the ball, it says 20 degrees east of north, right? 20 degrees east of north. So north and then 20 degrees east is like that. So there's 20 degrees and it's 35 meters per second. All right? So that looks really messy. Can't even read it. We do a better job at that. All right. There. All right? So what we want to get is the velocity of the ball relative to the ground. Okay? All right, so we got to, resolving the components, right? No kidding. So here's the y component, and there's the x component, right? So we already did this, but whatever. Okay, so velocity ball relative to the ground. The x piece is opposite, so it's sine. So it's 35. Again, I'm being lazy. Sorry, really. Man, I shouldn't be lazy. Whatever, I'm going to be lazy. 35 sine of 20 in the I direction plus 35 cosine 20, right? Adjacent cosine in the j direction. And we already did this, right? So it's 12I plus 32.9j. Okay? Which is, like I said, we already did that. Now, what do we want? We want the velocity of the ball relative to the, I'm going to say runner. Is that all right? Hope you don't mind. Okay, that's what we want, right? So again, just do your silly equation. So blank, blank plus v blank, blank. Right? Ball on the left, ball on the left. Runner on the right, runner on the right. What's in the middle? Well, it has to be ground. What else is there? So it's ground. Isn't that awesome? Silly equation is great. All right. Okay, so, but now you're going to see something a little interesting, though. Okay, let's just do it. So the velocity of the ball relative to the ground, wait a minute, is this, but hold it, just hold it a second. Let's just read this first. Velocity of the ball relative to the ground, I have it. But what's this? The velocity of the ground relative to the runner. What in the world is that? Well, I mean, think about it. Like if I'm going this way at 10 meters per second, according to me, according to my reference frame, what's the ground doing? It's going that way, right? Okay, so if the velocity of the runner relative to the ground is 10j, what is the velocity of the ground relative to the runner? It's minus 10j, okay? It's minus 10j, that's all. So that's all there is, really is to it, all right? Okay? So that's all there is to it. Okay, so we can do it now. All right, so let's do it. So the velocity of the ball relative to the ground is 12I plus 32.9j plus this, which is minus 10j, and that's equal to 12I plus 22.9j. And then it's all the same as the other one. Okay, it's exactly the same as before. So, whatever, you can do it, the first method or the second method, whatever you're comfortable with. It doesn't really matter. But you get the same answer, okay? That's the important thing. Okay, let's see. Where am I? All right. Okay. Now what we want to do is, okay, so like I said, so far, well, in this class, all we're talking about is Galilean relativity. And again, that means that the speeds that are involved in the problem are much less than the speed of light. But I just want to give you a flavor for this because it's kind of cool. All right? So, let's pretend, let's see if this thing works. Okay, so this thing, you probably can't see it, but this thing has a little laser pointer. All right, so the speed of the light coming out of my remote mouse here is the speed of light, right? Okay, all right, so let's pretend that I'm going to run towards you while I'm turning on my light, all right? While I'm turning on my light. So, according to Galilean relativity, what would you measure for the speed of light? Well, look. So velocity of light relative to u equals velocity of the light, this is L, relative to me plus velocity of me relative to you, right? I mean, that kind of makes sense, you know? Okay, I think that makes sense. All right, let's do it. So the velocity of the light relative to me is the speed of light, just c, okay? Yes, I need the vectors. And let's just say that I'm really fast in my dreams, right? Let's say the velocity of me relative to you is 10 meters per second. Well, then what is that? It's the speed of light plus 10 meters per second, right? Piece of cake, you know? Again, if you're in a car's going that way, no air resistance, you throw a ball. What's the speed of the ball relative to somebody on the ground? You add the speed of the car plus the speed of the ball. Same thing here, right? No kidding. Well, guess what? It's wrong. Okay, it's wrong. So when you do the experiment, the answer is the speed of light. And this doesn't, I don't care what this is. This could have been a rocket ship. In other words, you could have a rocket ship traveling at 99% of the speed of light. The rocket ship turns on a light, let's say, you know, and somebody on the ground measures the speed of the light. Come on, what would Newton say? Newton would say that the speed of the light is the speed of light according to the rocket plus the speed of the rocket. So that's 1.99 c, right? Common sense, you have to admit. You do the experiment, guess what? This guy would measure speed of light to be the speed of light. So in other words, the velocity of the rocket ship is completely irrelevant. Now, if that doesn't blow your mind, you don't understand what we're talking about, all right? Because it should totally blow your mind. Okay, so what are we saying? We're saying that every formula so basically, Galilean relativity only works for the velocity being much, much less than c. If the velocity is near c, you have to use relativity, physics 221. But again, this cool formula, these formulas we're going to use in physics 221. We're going to have to modify them. You know, we're going to have to have a denominator here. You know, so we're going to have to modify these things, but you know, we're going to use them. So it's totally cool. All right. Yeah. Okay. So here. So this is according to, so again, this is Einstein. He predicted this, but it's been shown over and over and over to be true. All right. So I don't care how fast the train is going to the right. I don't care how fast the runner is going to the right. The runner holding the flashlight measures the speed of light coming out of his flashlight to be the speed of light, lowercase c. This guy also measures the speed of light to be the speed of light. Doesn't matter how fast the runner's going, doesn't matter how fast the train's going. Crazy, right? Crazy. But it's true. What can you say? Okay, let's quit.